Okay, now let's look at an example and verify the bits of the theorem we saw in the previous video. So it's a completely made up example. I'm just going to imagine we've got these 5 different points in R2. Okay. I'm going to enter them into R, and we're going to look at their distances, and we're going to compute the various bits of the theorem to check that it's true. Okay. So I've got my matrix X here of points. The first one was 0, 0, second one 1, 0, third one 0, 1, so on. Okay. Now, there's an easy way to compute distances in R. We can use this dist command, and it returns to us a lower diagonal matrix of the distances. Okay, it doesn't give a distance between 1 and itself. It starts with a distance between 1 and 2. Okay. And we can see that from here. Look, the Euclidean distance between point 1, 0, 0 and point 1, 0 is going to be 1. Okay. Whereas the distance between point 2 and point 3, think about it, it's going to be the square root of 1 squared plus 1 squared, the square root of 2. That's what we get. Okay. Now, this command, you can put in different choices of distance here, but the default is the Euclidean distance, which is what we're using. Now, sometimes we're going to want the full matrix here, so we can do that by adding diag equals true. Okay, so that gives us zeros in the diagonal, and then we can put upper equals true to get the full matrix here. So let's call that our distance matrix D. So the first part of the theorem we had before was saying that if D is a Euclidean distance matrix, which we know it is because we've created it, okay, then the centered inner product matrix B here can be computed more easily in this way. Okay. And that, but thus B is positive semi-definite. So let's have a look at that. Okay. Let's first compute B using the definition. So to do that, I'm going to need to define the centering matrix H. Okay, so that's a diagonal matrix minus 1/5 times the vector of 1s times a row vector of 1s. Okay, it gives me this. And then we said that if we let A be minus a half times D times D, okay, we get this. And just note here that D times D with this multiplication sign gives us element-wise multiplication in R. Okay. To do matrix multiplication, you know you have to do percentage star percentage. Okay. But we want the Hadamard product here, so it's D star D. So we've got this matrix A here. So we have to do B, which is H times A times H. Well, that's giving me an error. Why is that? Well, I think it's due to the definition of D here. So let me just redefine D. Okay. So I needed to specify it as a matrix here. Okay. Then let's redefine A as this. And now this should work. Okay. So we've got this matrix B, the centered inner product matrix B. Now the first bit of the theorem said that B computed this way is HAH could be computed more easily as H times X times transpose of H times X. Okay, so they look a bit different when we first see them, but let's just round this off a bit. Okay, so I've just lots of these numbers are very close to zero. There's numerical error here, so I've just rounded them off. Okay, and you can see we've got the same thing here. B is the same as computing it this way. Another way of doing this, we could have centered X using the sweep command like we've used. Okay. And then if we do X times transposed of XC, sorry, we get the same thing again. Okay, so let's call this thing B2, just for later. So that's the first part of the theorem, okay, that we can compute B more easily in this way. And it also said that B is positive semi-definite, so let's check that. How do we check something is positive semi-definite? Well, we look at its eigenvalues. Okay. And we've got 2 positive eigenvalues here, and then we've got 3 eigenvalues that are 0. Okay, they're not exactly 0 because there's numerical error when we compute anything on the computer, but these are essentially all 0. Okay, so we've got 2 positives and the rest 0. So the rank of B here is 2. So this leads us to the second part of the theorem. Okay. So let's now imagine someone came along and gave us the distance matrix D and asked us to find coordinates. Well, the first thing we'd do would be to compute B in the way we just said. Okay. Then the theorem said, well, we can find a set of points in RK where K is the rank of the matrix. So in this case, the rank was 2, which we know is the case, right? Because we created the distance matrix in that case. We know we have 2-dimensional space. So the theorem says, though, that we can find points in 2-dimensional space, X, from the eigendecomposition by taking the eigenvectors times the square root of the eigenvalue matrix. So let's do that. So I'm going to store the eigenvalues in B.I here, eigenvectors on eigenvalues, and then I'm going to compute Y in the way specified in the theorem. So the square root was already there, wasn't it? I didn't need that extra square root. So we've got the square root of the eigenvalues, sorry, times the eigenvectors. Okay. So this gives me a set of points Y in 2-dimensional space. Okay. The first thing to note is that these are very different points. They're not the same points as we started with. But that's okay. We weren't trying to find the original point. We're just trying to find a set of 5 points in 2-dimensional space that had the right distance matrix. So is this the right distance matrix? Let's have a look. Okay, so that's the distances between the Y's we've just found, and the distances between our original X are the same. Okay, so this is what the theorem said. We can take our distance matrix, we can convert it to a centered inner product matrix, B, and then from B, by taking the eigendecomposition, we can work out a set of points Y that have the right distance matrix, that have the distance matrix D. Yeah. So we've not used the original data X anywhere here, we just used the distance matrix. We computed the set of points Y. So in this calculation here, I used the B defined as HAH. We could also use the distance matrix B2, okay, which I did by X, the centered version of X times the centered version of X. Okay. So let's just use that. I just want to do this just to show you that these calculations are not particularly stable. Okay. So if I do the eigendecomposition of this, I still get eigenvectors that are 2, 2, and zeros, but I get different eigenvectors this time. So if I compute my set of points here, I get a very different set of points to what I computed with Y. Okay. Now the distances still are correct. We've got the right distances, but they're just different points. Okay, so they look a bit more like the original points, yeah. But they're still different. Well, very different. They're -1s instead of 1s. But I know they're just reordered, aren't they? Yes, so they're the same set of points, just reordered as X. Look, okay. So there are numerical kind of instabilities in doing this. The key point is that it'll create us a distance matrix, a set of points Y that has the right distance matrix. So just finally then, I want to stress that there is an R command for doing this. We don't have to do this ourselves. Okay, so the R command is CMD scale, so classical multi-dimensional scaling. Okay. And what we do, we just return the we just apply it to the distance matrix D. And in that case, it gives us a set of points y.MDS here. Okay, so let's just plot all these points to see how similar or otherwise they are. Okay, so here I've got the original data points, the 5 original data points plotted. So this is data point 1, data point 2, 3, 4, 5. Here I've got the reconstruction we first did, y. Okay. Here's the second one, y2, and this is the one given by r. You can see they're all different. Yeah. These three are all on the same, got points in the same place, just reordered. But y has the points not aligned with the axes. But they have the same interpoint distances, so they are equally useful as a representation of the data. So again, just to stress what we've done here. We started with our matrix B, and we've computed a set of points X. And those set of point X have recovered, at least in terms of the distances, the original data. Because in this case, the original data, the original distance matrix, really did have a set of points corresponding to it in Euclidean space, okay, with Euclidean distances given by its distance matrix. Okay, so if we did this with the map data we had before, so if I applied this command CMD scale, a classical multidimensional scale command, to the distances, we get a map, not really a map of course, we get a set of points that looks like this. Okay. So if you go back to the map of England, if you're not from England, this you'll have to squint particularly hard at this, but if we go back to the map of England, you can see we've got Plymouth, London, Norwich on an axis here, right angles to Newcastle. And if we go back to what we've just found, here we've got the same kind of thing. Plymouth, London, Norwich, right angles to Newcastle. So the points, the cities are in the right location here. The map has just been rotated 90 degrees. So we've essentially recovered the map of England, yeah, just using the distances between the cities. Okay.